Okay, good evening, everybody, and welcome to another session of organic chemistry. In today's session, we are going to start our discussion on chapter 23 from your book, which is concerned with the chemistry of carbonyl condensation reactions. So before we start the session, let me make a few announcements. I do have your exam number 3 graded, and you should stop me about 5 minutes to the end of class today so I could give them back to you. Also, I want to remind you that the next class exam, which is exam number 4, is scheduled for about 2 weeks from today, which is April 25. So we only have about 2 weeks to cover 2 chapters. Okay. Okay, so that is exam number 4 on April 25. Now for the seniors who have to do 2 exams, they will have to do their final exam on Wednesday, April 24 at 6 p.m. in room G8. That is for the seniors. So for the seniors, your exam will be Wednesday, April 24 at 6 p.m. in room G8, and then you come back to take the exam number 4 on April 25, which is Thursday. Okay, so because I do have to send your grade to the registrar at the end of the day of on April 25. Okay. Also, for the homework assignment, the next homework assignment is due on Sunday, April 21st at 11 p.m. and that will be the end of chapter questions in chapter 23. Okay, and then next week we are going to have some online review session next week. So I will make those announcements next week. Okay, now to get the session started today, Lorenzo, go ahead. What are we doing today?
Alright, today's topics and concepts, we'll be going over carbonyl condensation reaction, Aldol condensation, intramolecular Aldol reaction, Claisen condensation reaction, intramolecular Claisen condensation, Dieckmann condensation, microreaction, conjugate addition, and Robertson annihilation.
Okay, thank you, Lorenzo. Okay, so just as Lorenzo has just informed us, we are going to go through all of these topics today. Believe me, most of these topics, you should not be intimidated by these topics, because most of the concepts and all reactions we have actually done before. So most of them will be very familiar to all of you. Okay, on the next slide, I would like to call your attention to what I call the learning outcome objectives. So you should use this list of items on this slide as a form of study guide to study for the content of this chapter. Now, I want to show you this molecule here, which is steron, adrenosteron. It is a steroid hormone which is used, of course, in weight loss and also for muscle enhancement. Now, why do I want to show you this structure? I am showing you this structure because at the end of this chapter, you should be able to make this kind of molecules, at least begin to have some idea on how to make this kind of molecules based on the chemistry that we have been teaching you thus far, particularly from this particular chapter. So you can see here There is no limit to what the organic chemistry can do. Starting from small molecules, you could actually build very, very important molecules indeed. Okay, so now the next question is, what is carbonyl condensation reaction? Carbonyl condensation okay, simply stated, I would define carbonyl condensation reaction as two molecules, two carbonyl containing molecules, joining together to form a bigger molecule and a smaller neutral molecule. And the smaller neutral molecule will be molecules like water, alcohol, such as ethanol, or methanol. In other words, we have two carbonyl containing molecules joining together to form a bigger molecule, and at the same time forming a smaller neutral molecule. Now the question is, how does this happen? How does this happen? Now to begin to show you this type of reaction, let us start with what we call the Claisen condensation reaction. Okay, I told you earlier, most of the concept and mechanism for this chapter you guys already know. So for example, supposing I give you this molecule here. This is a molecule of ethyl acetate. And then supposing I give you this ethoxide, which is a very strong base, what do you think will happen? What will happen? What do you expect to happen based on what we've done in the last chapter? We form enolate anion. Exactly. We form enolate anion. That is all we did in the last chapter. Enolate anion chemistry. Now, so in this chapter also, we are going to continue the enolate anion chemistry. So here, we form the enolate anion because the hydrogens here are fairly acidic. Okay, so we are going to abstract the proton from here, so therefore we form this here. We form that enolate anion, and in the process we're also going to, of course, form ethanol right here. Now supposing now we take this enolate anion, keep in mind the enolate anion here, this carbon here could act as a nucleophile. It could act as a nucleophile. Supposing now we take another molecule of ethyl acetate. Supposing we take another molecule of ethyl acetate. And then we take this enolate anion that we formed, okay? So this enolate anion wants to react as a nucleophile, and this carbonyl of the ethyl acetate, another molecule of ethyl acetate, is electrophilic. In other words, it could develop a positive character to it, thereby attracting a nucleophile, right? We all know that, right? Okay? So what kind of reaction do you think will take place between this nucleophile and this electrophilic carbon? What do you think will happen? Attack, right? Nucleophilic addition first, right? Okay, very good. So now we have this. That nucleophile attacks this electrophilic carbon here, and this pi electron goes to oxygen, and then what do we have as our intermediate? Let me show that we do have this non-bonding pair of electrons here to start with. And this is still here. Now we have joined this nucleophilic carbon to this here. So let me use a different color pen. Now what do you think is going to happen next? We're going to regenerate the carbonyl, right? Reform the carbonyl. You guys have done this before, so there is nothing new here. So therefore, we are going to end up with nucleophilic acyl substitution reaction. So we regenerate this, and in so doing, we know that this carbon cannot have more than 4 bonds. So what we give? The ethoxide will leave. Very good. And so we form this. To form that molecule. Plus, in the process we are going to lose ethoxide, okay? Okay, now see what has happened here. Do you recognize this molecule here? Do you recognize that molecule? What is it? That's acetoacetic ester, right? That is how we make acetoacetic ester. Now you see where we're going. Now those reactions we gave you in chapter 22, we could start from all the way from ethyl acetate, right? So this is kind of thinking you guys should be engaging in. Okay, so rather than starting the reaction from ethyl acetoacetate, we could start from acetic acid. Okay, anyway. So now you form this. Now because you have the ethoxide in solution, and you have this acidic hydrogen here, because this hydrogen here, what is the pKa value for this hydrogen? Any idea? pKa value? About 10? Okay, very good. So we say the pKa for those hydrogens is about 10. About the pKa for these hydrogens here? About 20? Okay. So about 20. So what is going to happen? So this ethoxide that is formed here will come here and abstract a proton from here. Okay? And so we get this. Let me just take this out of the way. So we can see that better. So now it comes in, abstract that proton, and then you form another inolate anion. We have this here. Then we have this. Plus we have ethanol. Okay, so that's how we are going to lose that small neutral molecule of ethanol. So finally, to stop this reaction, what do? We now add hydronium ion. Because we form an inolate ion here, to stop the process, we add hydronium ion. And the inolate that is formed here comes here to abstract a proton from the hydronium ion, and we end up with our final product, which is the ethyl acetoacetate. Now, this sequence of reaction mechanism I've given you here is what we refer to as Claisen condensation. In other words, you have two molecules of ethyl acetate, two molecules of an ester. The first thing you do, you form the inolate anion, and that inolate anion now acts as a nucleophile to attack another molecule of an ester, in which case that other molecule will provide the electrophilic carbon, in this case, which is this here, go through the intermediate, and finally, what is the final product? The final product is a beta keto ester. So your final product here is a beta keto ester. Okay? If you look at this carbonyl of the ester, if you say this is the carbonyl of interest, this is the alpha carbon, and this is the beta carbon. So that is why we say beta keto ester. Or if you want to look at it from the number point of view, say this is carbon 1, 2, and 3. So the carbonyl of the ketone and the carbonyl of the ester, they have a 1-3 relationship to each other. So that is the final product. Now, ordinarily, unless I ask you to give me the mechanism of this reaction, we could just easily do this. We could do this. Two molecules of ethyl acetate, I have here step 1, ethoxide. Okay, what does that do? From the inolate anion, right? Okay. Then I say step 2, hydronium ion. In other words, this reaction goes through all of the processes, the mechanistic processes, and once it gets to here, that is when you add the hydronium ion. Okay? So therefore, the product will be, in essence, what we have done here is to join together those two molecules, and in the process, we are eliminating a smaller molecule, which is ethanol. Okay? So if I just give you this here, and I give you this reagent, I say, give me the product. This is what you give me. Or I could give you the product, give you the reagent, I say, give me the starting material. Okay, those are the different ways we could ask you this question. Okay, let's give you a few more examples of the Claisen condensation. Supposing we have this. There are so many variations of the Claisen condensation that we are going to discuss. Supposing we have this, 2 molecules of ethyl propanoid, and I have this here. Step 1, and then step 2. Step 1, the ethoxide acting as a base to form the enolate, and then step 2, the adenine ion to stop the process, right? So what will be the product? What will be? Let us number this. Well, okay. This is carbon 1, carbon 2, carbon 3, right? Carbon 1. Okay, so we have carbon 1, carbon 2, and 3. So we are going to have this, and then of course this will be carbon 1, carbon 2, carbon 3. Okay. Then keep in mind that we are forming enolate on this carbon number 2. Okay, and that will be joined to the carbonyl of another molecule. So what do we have here? We are going to have this. This is also carbon 1, carbon 2, carbon 3. You see that? Okay, and that will be the product. Yes.
I don't get why the methyl group is acting as a...
Why the methyl this here?
Because if you go back to the last problem, it's like the CH2, which it just remains a CH2, I don't know.
Okay.
Yeah, why is that there?
Why this one here?
Like, why wouldn't it be CH2, CH2?
Okay, okay, okay. Okay, anybody follow that question? Okay, okay, let us see here. Let's go back to here. Supposing I have 2 molecules. Okay, I wrote the 2 molecules together. Let me write them separate. The question Valerie is asking, why this methyl here? Okay. Supposing I have them separate. Okay. Now I'm going to number this. Let us call this number 4, carbon 4, carbon 5, and carbon 6. Okay. Let us, at this point, this first step here, the ethoxide, what does it do? Abstract hydrogen from either carbon 5 or from carbon 2, right? Okay, let us say it as abstract from carbon 5 to form the enolate. Supposing you form this enolate here, supposing you form that enolate. Now, when you get to this product here, which carbon, carbon number 5, which carbon will it be attached to? It will be attached to 1, and that is what, okay, so let me change this here. So this is carbon 4, carbon 5, carbon 6. Okay, you just told me carbon 5 will be attached to carbon 1, is that correct? So where is carbon 6 going to be? You follow that? This is carbon 6. it's attached to carbon 5. Do you follow that? Okay. Everybody see that? You see that? Okay. Okay, because this carbon 6 here is attached to carbon 5, and that's what you still have here. So think about it this way. Say this is this molecule here, right? That is it right here. Okay, and this other molecule here, the one that acted as an electrophilic carbon, this here, okay, this here the ethoxy is gone, and that is this here, and that is what you have here, because the net process is electrophilic. I'm sorry, nucleophilic acyl substitution reaction. Yes.
If we do not stop reaction with H2O here, which hydrogen would be releasing next step? For example, if we continue as we did in the previous chapter.
If you continue.
From the H2O, H2, and which of the hydrogen will be in a way fine.
Okay. Don't forget, it is this here.
In this step, what is in the next step?
Okay, here, which one will form the enolate? Okay, it is this one here, carbon number 5. That is the one that is between the two carbonyls. Right. So, before you add the acid, this here will be the enolate carbon. Okay, then when you add the carbon, the dilute acid, you protonate this carbon here. Okay. Now, like I told you before, the Claisen condensation is a very generic reaction, also very versatile reaction. Okay, what I've just given you here is a simple case of Claisen condensation. We could also have what we call mixed condensation, Claisen condensation. We could have what we call mixed Claisen condensation. Okay, in that case, you are going to use two different esters. But what you want to do, in order for you not to get a lot of mixture, you want to ensure that one of the esters does not have an alpha hydrogen. Okay? So therefore, if you want to do a mixed Claisen condensation, I could do this here. I could start with methyl benzoate or ethyl benzoate, and then I do this ethoxide, step 1, and step 2, hydronium ion. Okay, what do you think the product will be? Let me number this carbon here. I will say this is, let's call this carbon 1 at this point. Okay, carbon 2. Let's forget the rest of the molecule. And let us call this here carbon 3, and let us call this carbon 4. Okay? In the product. Okay, now which carbon are we going to form the enolate ion from? Carbon 4. Because here, the methyl benzoate does not have an alpha hydrogen. So we cannot form an enolate there. So whenever you want to do a mixed Claisen condensation, you want to make sure one of the esters does not have an alpha hydrogen. Because if it does, then you are going to get a mixture of products. You don't want to do that. Okay. So therefore, once we generate the enolate anion here, this carbon will be attached to what carbon? In the electrophilic carbon. So the electrophilic carbon is carbon number 1. Very good. So therefore, this will be the product based on what you guys have just told us. Okay, so let us use a different color pen. Okay, so this is green. Okay, you agree with that? So that will be the product. Okay, supposing I use another ester, as we do this. Ethyl formic. That will be another good ester that will allow you to do a mixed Claisen condensation. And also now I do ethyl acetate again. And I go step 1, ethoxide, and step 2, aluminum ion. Okay, what will be the product? Let me number this carbon again. This is carbon 1, and let us say this is carbon 2, and this is carbon 3. Okay, which carbon are we going to form the inolate ion from? Okay, so this number 3 carbon will be your nucleophilic carbon, and therefore which will be your electrophilic carbon? Number 1. Okay, so we form the inolate on this carbon, therefore the product will be okay. So far so good, right?
I have a question.
Yes.
So you can only do the Claisen mixed Claisen condensation only if the alpha carbon has 1 hydrogen.
If the alpha carbon,
Has 1.
okay, at least if you want to use an ester as a source of the nucleophilic carbon, it must have at least 1 alpha carbon, because you have to generate the inolate anion by pulling off the hydrogen, the proton. Okay, anyway, so you are going to form this beta keto ester, okay? Let's call it a beta keto ester at this point. Now, so far I have given you simple Claisen condensation and mixed Claisen condensation. It is also possible to use an aldehyde or a ketone as a source of nucleophilic carbon in Claisen condensation. The only requirement in Claisen condensation is the electrophilic carbon must be an ester. Okay? So let me write it. Only requirement in Claisen condensation is that the electrophilic carbon must be an ester. Okay, for example, I will take this. Okay, I take acetone, which is a ketone, right? And what do I get when I react with the ethoxide?
Inolate.
I get the inolate. Okay. Now, supposing now I take that inolate, and now take this ester, I take that ester, right? Once again, this is the ethyl benzoate. And now I take the inolate from the acetone that we just generated. Okay. What do you think is going to happen? What will be the product? Let us number this here. Say this is carbon 1, and we call this carbon 2, carbon 3, and carbon 4. Okay, so this is step 1, of course. Okay, and then of course you also have here a oxide here. And then step 2, aluminum ion. Okay? We have the inolate ion on carbon 4, and so the product will be, the carbon 4 will be attached to which carbon? Carbon number 1. Okay, so therefore. So therefore, we also call this a Claisen condensation reaction. The only requirement is the electrophilic carbon must come from an ester. The nucleophilic carbon could come from anywhere. Okay? Nucleophilic carbon could come from anywhere. For example, supposing I have this. Yes. You don't need to do what? You don't need the ethoxide? We did. The ethoxide is here. Oh, in the final product. We form the ethanol.
No, I mean, you don't have ethoxide.
Where?
Like, I mean, like in the final molecule. So, like what we did earlier, we only have ethoxide in the final product.
Because, yeah, we don't, because this is the molecule we're starting with. Yeah, look, okay, I see what you're saying now. This is what we are starting with. This is our nucleophilic carbon. So you cannot have the, it's not an ester, it's a ketone. So that is why you have this here. You follow that? So you do not have to always make an ester. Your question is, must it always be an ester? No. It's not always going to be a keto ester. It could be a diketone. A diketone. In this case, this is a beta diketone. But the most important aspect of the Claisen condensation is the nucleophilic carbon, the electrophilic carbon must come from an ester. Okay? Okay. Now, let us give you another example of a mixed Claisen condensation. Supposing I have this, supposing I have that, and then I have this here. Step 1, acetaldehyde mixed with ethoxide. So what would that give you? Ethoxide with acetaldehyde, what will it give you? You get inolate, right? And then step 2, once you have this in solution, you have this starting material, this ester in solution, then followed by aluminum ion. So what will be the product? Here. Okay, so the product will be okay. So now you get a better dicarbonyl compound. Not necessarily must you always have beta keto ester. It depends on what you start with. Okay. Now we could also have what we call intramolecular Claisen condensation. Intramolecular Claisen okay, which we refer to as Dieckmann cyclization. Okay. Okay. Go back. Okay.
Okay, so the CH3 on the nuclear file attacks the electrophile, right? How come that wouldn't remain as CH3? Why does it become?
Why does it work?
Actually, never mind.
Okay, this here.
Sorry, I know what it is.
Like
Because I was trying to, you said earlier how carbon 6 remains a methyl, like it was the instrument of SCY, because that's the one that's directly affected.
Exactly. Okay, very good. Okay. So now let us look at intramolecular Claisen condensation, which we call Dieckmann cyclization reaction. Supposing I have this. How many carbons do we have in this molecule? 1, 2, 3, 4, 5, and 6. Okay? And then we have the reagent for Claisen condensation. Step 1, ethoxide, and step 2, hydronium ion. Okay? What do you think is going to happen here? What does the step 1 ethoxide, what will it do? It will abstract a proton from where? Which carbon? For either 2 or 5, because this is a symmetrical molecule. Very good. So you are going to form enolate anion either on carbon number 2 or on carbon number 5. And once you do that, what happens? That then attached here, let us assume that we form enolate anion here. Okay, and then what does it do? It simply will come in and attack the electrophilic carbon, which is carbon number 1. Okay, and in the process, of course, the ethoxide will leave finally, so you are going to get this product, a 5-member ring. You form that. You see that? Okay, so let us number the carbons again. This is carbon 1, 2, 3, 4, 5, and carbon 6. Okay, so in this case, you form a 6-member beta-keto cyclic beta-keto ester. Supposing you start with this. Okay, how many carbon do we have in that chain? 1, 2, 3, 4, 5, 6, and 7. Okay? So what will be the product? A 6-member ring, exactly. Step 1, step 2. So in this case, we are going to form a 6-member ring beta-keto ester. Okay? Now, supposing I give you this molecule. We are still on Claisen condensation. Okay? Take carbon 1, 2, 3, 4, 5, 6, 7, and 8. And I tell you to use this molecule here to give me a Claisen condensation. Okay? Use this molecule here to give me an example of a Claisen condensation, or an intramolecular Claisen condensation, which is Dieckmann condensation. Okay, which carbon will be your nucleophilic carbon? Which one? Why? That is correct. Why? Exactly, because the electrophile must be from an ester. The electrophilic carbon must be from an ester. So therefore, carbon number 6, this carbon here, will be your nucleophilic carbon. Yes. Yes, it could be A2. In that case, forms an 8-member ring. Generally, when you are doing cyclization, 6-member rings are better. They are preferred over 8-member rings. And both 5-member ring and 6-member ring are preferred always. Okay. Yes. It will also be 8. In this case, we are going to use 6. So 6 here will be your nucleophilic carbon. So once you form the enolate ion on that carbon, then that becomes your nucleophilic carbon. And of course, carbon number 1 of the ester this here becomes your electrophilic carbon. Okay. So therefore, the product will be a 6-member ring and this here will be, this carbon is this, and of course this is this here. Okay, let us number the carbons. This is carbon 1, carbon 2, 3, 4, 5, and this is carbon 6, where you form your enolate, and this is your carbon 7, and this is your carbon 8. Okay? So once again, what have we done here? We have formed a beta diketone. Okay? The most important feature here is your nucleophilic carbon could come from any molecule that is capable of generating an enolate anion, but your electrophilic carbon must come from an ester, if you have to call that a Claisen condensation. Okay, so I think we have done enough on Claisen condensation by now. Okay, now let us go to another set of reactions. Now this is called the Aldol condensation or Aldol reaction. In the case of the Aldol, similar to what you did with the ester. In this case, you start with either a ketone or an aldehyde. That is the difference. Okay, in the case of the Aldol, the electrophilic carbon must be from a ketone or an aldehyde, but the nucleophilic carbon could come from anywhere. Okay, so for example, supposing I take this. Here, I use hydroxide. This is generally a reversible process in the Aldol reaction. So you form your enolate. In this case, enolate of acetaldehyde. Okay. Now, once you form the enolate, then you have another molecule of acetaldehyde. Acting as a source of electrophilic carbon. Okay. And then what happens? This here comes here. Attach the electrophilic carbon. My electron goes to oxygen. And so what do we have? We have now we have so now this alkoxide that is formed, intermediate alkoxide that is formed, what happens is, because we have water in the system, comes in and abstracts a proton from water. To regenerate the hydroxide. Keep in mind the hydroxide is simply acting as a catalyst in this process. Okay, so we are going to regenerate the hydroxide. So you form this intermediate here. So what we form there, we form a beta hydroxy aldehyde. a beta hydroxy aldehyde. Okay? In essence, we have an alcohol and an aldehyde. And that is why we call it an aldol. So that is how we derive the name aldol. Alcohol and aldehyde combined. So the product that you get here, you get a product of what we call an aldol, which is a beta hydroxy. This is the alpha carbon relative to the carbonyl, and this is the beta carbon relative to the carbonyl. So you form a beta hydroxy aldehyde in this case. And now what happens, this reaction, if you simply just apply heat, and sometimes you may not even have to do that. What does it do? To form what we call a beta and alpha beta unsaturated aldehyde. So you are going to lose this hydrogen here and this hydroxide here in form of water. So you end up with this is so the product plus water, you lose water. So the product of the Aldol condensation, you form an alpha beta unsaturated aldehyde or ketone. In this case, aldehyde. Now, this reaction has become a generic reaction that we could actually use a ketone for the same reaction, and we still call it an Aldol condensation. Okay? So what is the next process here? You start with an aldehyde or ketone. You use catalytic amount of hydroxide in water. You end up with an alpha beta unsaturated aldehyde or ketone. Okay, let's give you couple of examples. Then do it out. Okay, thank you. Supposing I have it, instead of using an aldehyde, supposing I use a ketone. Two molecules. Catalytic amount of hydroxide. Okay? Okay, let me just number this. Say carbon 1, carbon 2, carbon 3. Let me make it easy for you. Okay, so let's use those two molecules separate. Another one here. Okay, let us call this carbon 4, carbon 5, and carbon 6. Okay? The first thing that happens here is what? With the hydroxide. Inolate on what carbon? Inolate on 1 or 4 if you choose any one of them, right? Okay? So let us say we choose 1, inolate. And then once we form the inolate, okay, and the product will be, what carbon will the carbon number 1 be attached to? Carbon number 5, right? Okay? Because this becomes your electrophilic carbon. So therefore, what are you going to get? You get this. And then I have, let me change this different color. Okay, now this here, this. So I say this is carbon number 4, according to you, carbon number 5, carbon number 6, and this is carbon number 1. You form the inolate on that, carbon number 2, and carbon number 3. Okay? At this point, we have formed the aldol. We still call it an aldol, even though we are using a ketone. Okay? So, yes.
Why couldn't the anion on the carbon sphere?
Yes, it could be.
Oh, okay.
It doesn't matter. It could be.
Okay.
As long as you follow the sequence, once you form, if you could form the anion on 3 or 6, it could be the same thing. Okay. So now when you do the dehydration, you apply heat, do dehydration, you are now going to form an alpha beta unsaturated ketone. So where would the double bond be? Can you give me the position?
5.
Between carbon 1 and 5, exactly. So the double bond will be here for the conjugation. Very good. Okay. Now we could also have a mixed aldol condensation. We could also have a mixed aldol condensation. Now, if you want to do a mixed aldol condensation, you follow the same requirement, the same guideline as we did in the case of the Claisen condensation. And what was that guideline that we gave you? Yes. The electrophilic carbon must not contain alpha hydrogen. Okay, no alpha hydrogen, right? In other words, one of the molecules, okay, the electrophilic carbon, in this case, the electrophilic carbon must not contain an alpha hydrogen. Okay? Keep in mind in this also, the electrophilic carbon must come from either a ketone or aldehyde. The nucleophilic carbon could come from anywhere. Okay. Let us see here. For example, for mixed aldol condensation, we could start with this. Okay. So this here, this aldehyde, this carbon therefore would be your electrophilic carbon, right? And we could use, for the nucleophilic carbon, we could use this acetone. And then we have hydroxide in water, okay? And what would be the product? Of course, the product would be this here. Let me go ahead and label the carbon again. So this is carbon 1 right here, which will be our electrophilic carbon. Let us say this is carbon 2, carbon 3, carbon 4. If we assume that carbon 2 will be your nucleophilic carbon, and that is where you remove the proton in order to form the inolate anion. Therefore, this here is carbon number 1, and this is your carbon number 2, carbon number 3, and carbon number 4. Okay, you follow that? Okay, so this is the case of mixed aldol condensation. You could also have intramolecular aldol condensation. Intramolecular aldol condensation. Okay, what I want to do here, I want to give you the same molecule that I gave you for the intramolecular Claisen condensation. Then I will ask you the same question. Okay, supposing I give you this molecule here. Okay, let us go ahead and label this. Let's say carbon 1, 2, 3, 4, 5, 6, 7, and 8. Okay? I wanted to use this molecule to give me an example of an aldol condensation reaction. The question is, which carbon will be your nucleophilic carbon? And which carbon will be your electrophilic carbon? Which will be, let's do the first one. Which will be your nucleophilic carbon? Which one? 2, exactly. Why 2? Because you form the inolate ion on these 2 here, and in order for you to call this an aldol condensation, the electrophilic carbon must be what? Must be either ketone or aldehyde. Okay, those are the guiding principles here. So therefore, you form your inolate here. You form your inolate on this carbon here, and then once you do that, then the carbon number 7 becomes your nucleophilic and electrophilic carbon. Okay? Yes.
So you form the inolate ion on the ester?
Yes, on the ester, yes. In this case, the inolate ion will be your ester, if you want to call it an aldol condensation. But if you wanted to call it a Claisen condensation, then it's the reverse, right? Okay? Okay, so in this case, sorry about that. Okay. In this case, since we want to use this molecule to give an example of intramolecular aldol condensation, we are going to form the inolate ion here, and that inolate ion will come in and simply attack this here. Okay. So we are going to form what? How many carbon in the ring system? How many? 1, 2, 3, 4, 5, 6. 6-member ring. So therefore. Okay, let's show the aldol first. Let us show the aldol first. Okay, so we have the aldol. It's right here. Let us see here. If we say we formed that, so this will be here. And therefore, this is going to be here. So you form the aldol. And then you do dehydration on the aldol. Do dehydration on the aldol, therefore you are going to form this here. From your alpha beta unsaturated carbonyl compound. So therefore, when we talk about all of these reactions, your imagination is just the limit here. You could almost do anything. The only thing you need to keep in mind is, whenever we say we have aldol, electrophilic carbon must come from a ketone or aldehyde. And on the same token, if we are talking of Claisen condensation, the electrophilic carbon must come from an ester. Okay? Now, supposing we have this. Supposing we have this. So if I have this here, you guys know this molecule already. Okay? You know that molecule, right? That's ethyl malonate. We can control this. Okay? And then we have this. Okay, what do you think the product will be if we want to call this an aldol condensation reaction? If we want to call it an aldol condensation reaction, what do you think the product will be? Okay, let us go ahead and label all of this here. It's carbon 1 here, carbon 2, carbon 3. What do you think the product will be? Let's draw the product of the aldol first, right? Okay, the aldol will be this here. And then from the malonate, we have this here. Okay, do you see that? Okay, in this case, the enolate from the malonic ester is acting as a nucleophile, right? And the carbonyl of acetaldehyde right here, carbon number 3, is acting as an electrophilic carbon. Yes.
So the enolate will be on the malonic ester?
Yes.
The enolate carbon will be on the dimension.
Well, the enolate is on this here.
Yeah.
The enolate is on this carbon.
It will be CH, right?
Oh,
That's CH2.
The enolate is on this carbon.
okay.
So it should be
Right?
CH, right?
Huh?
Should it be CH?
Oh, I'm sorry. Sorry about that. Thank you. Okay, so the enolate is on this carbon here. Okay, and then this becomes your electrophilic carbon. So you get it. Now, once you apply the heat, what do we get? To get the complete aldol condensation, you're now going to form, this is your alpha carbon, this is your beta carbon. You will form a double bond here, right? Okay? So that becomes okay. So once again, your own imagination is the limit to what you can really do with this reaction. One more reaction before we go. What time is it? Okay, oh, it's almost time. Okay. I think we are going to continue on this chapter, and then there will be a 10-minute quiz on Tuesday when you come on Tuesday on what we did today. Okay, so let me give you back your exam paper.